Let's learn a little bit about exponential functions now. I want to contrast the idea of a polynomial, or more specifically, a monomial, and compare that to an exponential function. Now, these guys look similar, but they're quite different. A polynomial or monomial, meaning that there's just one term, would be something like x squared, whereas an exponential function would look something like 2 to the x. And what we could see is that in a polynomial, the variable is not in the exponent. However, and you have a constant for the exponent. In an exponential function, it's reversed. You have a number downstairs, so we call this number the base, and you have the variable actually in the exponent. So that's really what defines an exponential function, is the variable is in the exponent. So let's take a look at a graph. So what I've done here is I've created a table of values. So just to make it perfectly obvious, we're going to take the x value of -3. We're going to have 2 to the -3. And when we evaluate that, we're going to get this 0.125. So if we insert different values of x, like -2, -1, 0, 1, 2, 3, and then we plotted what each of those values were, we would get the curve that you see above. So one interesting thing to notice is that 2 to the 0 power is equal to 1, so our y-intercept is going to be 1. Another interesting thing to notice is that it appears we're going to have a horizontal asymptote over here just by looking at our graph. We notice that this function is increasing the whole time. And one nice thing about seeing that this increases the whole time is that this is the graph of a one-to-one function. In general, when the base b is greater than 1, then we're going to have a graph that has this general shape. So larger bases are going to slope up more quickly to the right of the y-axis, and it's going to decrease more quickly to the left of the x-axis when b gets bigger and bigger. Let's take a look at another example. Let's look at a different example over here. This time our base b is equal to 1/2. So we can see that right here. And again, we create a table of values. So this time I'm going to have my x values still range from -3 to 3. And I'm going to insert each of those values into my exponential function and look at the output values over here. Okay, so when I plot each of those values, you can see at -3, we go up to 8. And then at -2, we go up to 4. And -1, we go up to 2, and so forth, so on and so forth, right? So when we look at this graph, what do we notice? One thing we notice is that, oh, this function looks like it's decreasing. So I could write that down here. So it's decreasing. We notice that this guy is also one-to-one, and we know one-to-one means that there is an inverse, right? We can see that we again have a horizontal asymptote over here, which is going to be that's the x-axis. So I could label the asymptote as y is equal to 0. And one thing you'll notice is when you look at the comparison between each of these two graphs, they look very similar to each other, right? In fact, it looks like the second graph is just a reflection of the first graph. So It looks like if we had, 1/2 to the x power, and then you compare that to 2 to the x power, the relationship is that it's just reflected about the y-axis. Now, this shouldn't be a surprise to us because we can really rewrite this guy as 2 to the -1 raised to the x power, right? And then if you wanted to, you could write that as really 2 to the -x. So we're really comparing 2 to the -x versus 2 to the x power. And when you look at this, we're just multiplying the x coordinate by -1. So that action of multiplying by the x coordinate by -1, this is what causes the horizontal reflection. Okay, let's piece all this together in a theorem here. So in our theorem, the first thing we have is we have some restrictions on the base. So the base must be greater than 0, and it's not allowed to be equal to 1. So when the base is 0 or 1, those are, degenerate cases. Another thing we notice is that when you have this exponential function, your function is going to be a one-to-one function. And let's say that you have the domain is going to go from -infinity to +infinity. And the range is going to be only positive values, so from 0 to +infinity. Okay. When we look at the different cases of the base, actually, this is the second graph that we had looked at. So the one we looked at was the base was equal to 1/2. But when we have that base is between 0 and 1, we saw from our previous example that we're going to have a decreasing function. And when the base is greater than 1, then your exponential function is going to be increasing. And we saw that on our previous two examples. Now, the next thing we want to look at is we want to look at properties of the exponents. So let me zoom in here a little bit. These are going to be important when we study the laws of logarithms. So we really want to really keep a close eye on this. So what happens when you have two numbers with the same base and you multiply those two guys together? The net effect of multiplying two numbers with the same base is you're going to add the exponents. Okay, so that's really a key property here. You got two things, you got to add the exponents there. All right. What happens when you have this subtraction scenario? This subtraction really corresponds to not the product, but it corresponds to the division. So we're going to have b of x divided by b of y. When you have two things with the same base, but you're dividing the two, what you end up doing is you end up subtracting the exponents. Okay. And what happens when you have a power to a power? Well, when you have a power to a power, what you're going to do is you're going to actually multiply the exponents. Okay. So if I look here, oh, you got one power, b to one power, and then you raise the whole thing to another power, that's going to multiply the exponents. And then the final property that we have is that if you have two different bases to the same power, you basically distribute the power. So this becomes a to the x times b to the x. Okay. So I want to take a second to make a quick note here. I want to point out that 1, 2, and 3 are important when we study laws of logarithms. Okay.